Section 4.6, Solution Stoichiometry. Stoichiometry is used to determine how much of a particular something is needed to react with or is produced in a chemical reaction. When we studied stoichiometry in Chapter 3, we used a set pattern to solve those problems all the time. Sometimes we had to use those steps, sometimes we didn't. Solution stoichiometry does the same type of thing. In solution stoichiometry, step number one is always to make sure that you have a balanced chemical equation. Sometimes it's given to you, sometimes it's not. The second step is, when in doubt, convert to moles. And since we're talking about solution stoichiometry, most of the time we're going to end up using the molarity triangle. Molarity equals moles divided by liters, usually solving for moles. Or occasionally you'll be given grams and you have to go to moles, or you're given a number of particles and have to go to moles. Third step is used to mole-to-mole ratio from the balanced chemical equation. And then lastly, sometimes you have to do step 4, sometimes you don't, is convert to a particular set of units, usually using the molarity triangle once again, occasionally using the same type of thing right here where you go from moles to grams or from moles to number of particles. So these same 4 steps are generally used in solution stoichiometry, but sometimes it seems a little bit more confusing because we're talking in terms of solutions now, and the molarity triangle usually takes precedence for converting to lots of things. So there's several different types of solution stoichiometry problems that are emphasized in the text, and one of them is called a titration. A titration is used to determine the concentration or volume of a particular solute in a solution, and what happens is you usually end up using a reagent that's of a known concentration called a standard solution. Titrations can be conducted using acids and bases, precipitation reactions, or oxidation reduction reactions. The ones that you traditionally see in an introductory chemistry class are acid-base titrations, but we'll see several oxidation reduction titrations in this or the next video cast. An important point during a titration is one called the equivalence point, and the equivalence point is when the moles of one substance, if it was an acid and base titration, and in this case it would be the moles of the acid, are equal to the moles of the base. So the moles of the one thing are equal to the moles of the other thing that we're looking for. And when this is the case, it makes the problem fairly easy to solve, but they use a fancy name to say, when are you at an equal number of moles point? Sometimes this is also called the neutralization point, or neutralizing point. Neutralizing point of a chemical equation, especially when you're talking about acids and bases. It could be a neutralized point for a precipitation reaction too, if you're talking about like all of something is used up. So let's work some sample problems using solution stoichiometry, and I'll try to point out some pitfalls along the way for ones you might encounter. Make sure that you have this sheet of paper out and you can follow along with it, and have your periodic table and calculator along too, and you can try them as well. Sample exercise 4.15. How many grams of CaOH2 are needed to neutralize 25 milliliters of 0.1 molar HNO3? Step number 1, write the balanced chemical equation. If you don't know how to do that, then you're probably not going to do too well on any of these problems. So let's do it together. Calcium hydroxide, and we're going to react it with HNO3. And when we do this, we're going to get some calcium nitrate over here. Remember, calcium is plus 2, nitrate's minus 1, so you're going to have to drop and swap there. And then you get some HOH, or some water over here as well. And then to balance this critter, we're going to need 2 waters, and we'll also end up needing 2 HNO3s. So notice our ratio right here of this strong base to this strong acid is a 2-to-1 ratio. Anyway, they ask how many grams of CaOH3 are needed to neutralize this many milliliters of 0.1 molar. So if you're going on from step number 1, once you have the balanced chemical equation, what do you need to do? Well, you need to convert to moles. And we're given information right here to use the molarity triangle, because we're given a volume and we're given a molarity. So molarity is equal to moles divided by liters. And if we want to find moles, remember, we just take molarity times liters. Molarity times liters is equal to moles. And our molarity is 0.1, and our liters are 25 milliliters, so 3 to the left, 1, 2, 3, 0.025 liters. So 0.1 times 0.025 is 0.0025 moles. That's how many moles of HNO3 that we have. So we know the moles of HNO3. Step number 3, mole to mole ratio from the balanced chemical equation. So now we can take our 0.0025 moles of HNO3. Notice I put my units in first before I put numbers in. Put moles of HNO3 in a position where it's going to cancel. The thing I want to know is CaNO3 so I put that on the top in a new position. Notice the ratio here is 1 to 2. 2 goes with the HNO3, 1 with the CaNO3, 2. And it asks how many grams are needed to neutralize. So step number 4, once I've done the mole to mole ratio, is convert to the asked for units. And in this case, they asked for grams. So I'm going to go from moles to grams. And to do that, remember, I need to use the periodic table. So if I look on the periodic table for calcium nitrate, I'll put grams of calcium nitrate as my new set of units and moles of calcium nitrate down here. And in 1 mole of calcium nitrate, if I add it up on the periodic table, calcium, of course, is 40, nitrogen over here is 14, and then oxygen is 16. And if I look at the formula, notice it's CaNO3, 2, so there's 2 of those nitrates here. And if I add those guys up really quick, I find out that there's 74.1 grams in 1 mole. And notice my 1 to 2 ratio, and when I multiply those guys together, I end up with 0.0926 grams of calcium hydroxide that would be needed to neutralize, or we could also say reach the equivalence point if we wanted to use the fancy new word that we learned. Practice exercise 14.15. How many grams of NaOH are needed to neutralize 20 milliliters of 0.15 molar H2SO4? To do this problem, it is good to first of all write the balanced chemical equation. Step number 1, we have 2 NaOH plus H2SO4 goes to 2 waters and Na2SO4. I just wrote the balanced equation. I didn't even do any explaining. So if you want to go back and not have the 2's in there, go ahead and balance it yourself. Notice the Na and the H swap positions right there. That's step number 1, write the balanced chemical equation. Second of all, we need to convert to moles. We're told that it's 0.515 molar and there's 20 milliliters. So 0.15 moles per liter multiplied by my liters, 1, 2, 3 places to the left, so 0.02 liters. And when I multiply those together, that gives me 0.003 moles, 0.003 moles of the H2SO4. That's step number 2. So following along with my steps once again, balanced chemical equation. Second, convert to mole. I use the molarity triangle. Third, mole to mole ratio. And then fourth, convert to the asked for units. So I'll take my 0.003 moles of the H2SO4. Put H2SO4 in a position where it's going to cancel. And the thing that I want to know is NaOH. So put NaOH as my new set of units. Notice there's a 2 in front of the NaOH and a 1 in front of the H2SO4. And then lastly, I'll convert to grams. Notice my H2SO4 cancels with my H2SO4. Another good reason to put your units, or at least what the substance is that you're that you have, so then you can put it in a position where it's going to cancel. There's 40 grams in 1 mole of NaOH if you add it up on the periodic table, and so that turns out to be 0.24 grams of NaOH. A very similar problem to the one that we just did above. Next problem. How many liters of 0.5 molar HCl are needed to react completely with 0.1 molar PbNO3? Notice here we don't have just an acid-base reaction here. We've got an acid going along with lead nitrate here. So we're going to make like a precipitation reaction actually here, where we take HCl and we're going to react it with some lead nitrate. And then we'll swap the partners right here, and we'll get some PbCl. Notice it's lead 2 because nitrate's -1 and there's 2 of them. So PbCl2 plus my HNO3. Then to balance this chemical reaction, I'll need a 2 here. That gives me 2 hydrogens, also the 2 chlorines that I need. So I'm going to need to put a 2 here in front of the HNO3 to make sure that I've got the right number of nitrates, because I need 2 of those and 2 hydrogens. So that's step number 1, balance chemical equation. Step number 2 after that, convert to moles, probably using the molarity triangle, then mole to mole ratio, then convert to units. So we're told that we have 0.5 molar HCl, and it asks how many liters of that do I need. And it tells me that there are 0.1 moles of PbNO3. Hey, this is handy. 0.100 moles of PbNO3. Guess which step I don't have to do? Yeah, it's the convert to moles step, because they already told me the number of moles. So forget the molarity triangle stuff. Let's move on to step number 3. Told me how many moles I had. Go to step number 3, mole to mole ratio. Put the units that you have in a position where it's going to cancel. PbNO3, 2 in a position where it's going to cancel one of those. For the thing you're looking for, how much HCl is it? For 2 HCl's. Okay. And then lastly, it says how many liters are needed. So if I stop right here, I'll get my moles of HCl. And somebody might jump up and down and say, how's that going to help me? Well, remember the molarity triangles. Molarity equals moles divided by liters. Molarity equals moles divided by liters. And if I want to know liters, that equals moles divided by molarity. Well, I know the molarity right up here. I know the moles from right here, so I can divide those two and then I'll get my liters. So 0.1 times 2 is 0.2 moles of HCl. So if I want to know my liters or my volume, that's equal to my moles, which is 0.2 moles, divided by my molarity, which is 0.5 molar or moles per liter. 0.2 divided by 0.5 ends up being 0.4 liters. 0.4 liters. Okay, moving on. Some other practice exercises. Let's look at a couple more examples. Turn the page. This one says, if 25 milliliters of a 0.1 molar HBr solution is titrated with a 0.2 molar NaOH solution, how many milliliters of the NaOH solution are required to reach the, here's the word, equivalence point? Okay, now equivalence point is when the moles of the acid are equal to the moles of the base. The moles of the acid are equal to the moles of the base. And so if they're both solutions and you're given the volume and the concentration of one or both of them, and you're kind of an astute studier of the molarity triangle, molarity equals moles divided by liters, you could actually write a neat equation for this, as long as you know the acid and the base react in a 1-to-1 ratio. And remember, our first step in doing a solution stoichiometry or any stoichiometry problem is to write the balanced chemical equation. So let's do that really quick, and then I'll show you the neat trick that you can do along with it. HBr reacts with NaOH to form NaBr and HOH. So if you see that everything's balanced, it's a 1-to-1 ratio right here. So I know that my moles of acid will directly be equal to my moles of base because they're a 1-to-1 relationship when we're at the equivalence point. Now if you solve the molarity triangle for moles, cover up a mole, it equals molarity times liters. So what I could do is I could replace moles with molarity of acid times the volume of the acid is equal to the molarity of the base times the volume of base, because moles are equal to molarity times liters. And then it simply becomes an easy plug and chug, and you can actually skip step 2, 3, and 4 and just solve for the thing that you want to know. Because what do they want to know? How many milliliters? Well, that's volume right here. So my molarity of my acid is 0.1 molar. My volume of my acid is 25 milliliters. This also makes it really handy because I don't have to convert to liters. And then my molarity of my base is 0.2 molar. and my volume of my base is what I want to know. So dividing both sides by 0.2, so these guys cancel over here. 0.1 divided by 0.2 is the same as saying 1/2, and 1/2 of 25 is equal to 12.5 milliliters. So I can find my volume there fairly easily by using this relationship. Now remember, that only works if it's a 1-to-1 ratio in the balanced chemical equation, because otherwise you won't have equal moles of it. You'll actually double the number if it's a 2-to-1 ratio. So you still could use this kind of thing, but it becomes kind of shaky. So this is good for 1-to-1 ratios. Last one in this video cast, let's do this sample exercise 4.16. It says the quantity of chloride ions in a municipal water supply is determined by titrating the sample with silver, the silver ion right here. The reaction taking place during the reaction is blop plus blop equals silver chloride. The end point for this titration is marked by a change in color of a special type of indicator. And indicators are used a lot in titration reactions because they'll indicate when an equivalence point is reached. In acid-base reactions, you can see on page 153, they use an indicator called phenolphthalein, and we'll actually use some in class when we do a titration as well, like that. How many grams of chloride ion are in the sample if a sample of water if 20.2 milliliters of 0.1 molar silver ion is needed to react with all of the sample, with all of the silver in the sample, with all the chloride in the sample, I'm sorry. So step number 1, write the balanced chemical equation. That's done. Second of all, find your number of moles. So moles are equal to, what information are we given? The volume right here, and we're also given our molarity right here. If you remember the molarity triangle right up here, moles are equal to molarity times liters. So our molarity is 0.1 molar times our liters, which 1, 2, 3 places to the left really quick, is 0.0202 liters. And if you multiply those two together, we end up with 2.02 times 10 to the negative third moles of silver ion. And then we take our silver ion and go on to step number 3, which is the mole-to-mole ratio from the balanced chemical equation. And then we'll convert to our units. So I'll rewrite it over here. 2.02 times 10 to the negative third moles of silver ion. Put silver ion in a position where it's going to cancel. And then put the amount of chloride ion up here that I want to know. And the ratio happens to be 1-to-1. And the question was, how many grams of chloride ion are in a sample? And so what I need to do now is convert from moles of chloride ion. Notice my moles of silver cancel with my moles of silver, to grams of chloride ion. Now a lot of people would say, how do I go to grams of an ion? Well, what is an ion? An ion is something that has gained or lost an electron. How is gaining one electron going to affect the mass of just a chloride atom? Well, remember, atoms are mostly made up of the mass of the protons and neutrons. Electrons are like 1,000 times smaller, so it doesn't matter whether it's got a positive 1, negative 1, negative 2, negative 3 charge, something like that. You can still look on the periodic table and look up how, and you'll still get a very good approximation by saying that chloride ion has a mass of 35.45 grams. 35.45 goes right in here in 1 mole. And if I multiply those critters together, I end up with 7.17 times 10 to the negative 2 grams of chloride ion in there. So going through those steps once again, we did the balanced chemical equation that was given to us. We converted to moles using the molarity triangle. We used the mole-to-mole ratio from the balanced chemical equation. And then we converted to the units. And actually what they asked for here, they asked for grams. Part B. If the sample has a mass of 10 grams, what percent chloride ion does it contain? Well, to find percent of a sample, remember you take part divided by whole times 100%. So what's our part? Well, 7.17 times 10 to the negative third grams, we get that from right up here, divided by the whole sample, which is 10.0 grams, and then we'll multiply that by 100%. And if you take this number divided by 10 times 100, we end up with 0.717% chloride ion in the sample. Good luck with your solution stoichiometry problems.